Okay, so thank you very much for coming. It's my pleasure to be a part of this committee that's going to be evaluating the PhD thesis of this, candidate Venkatesh Kadandale. And thank you very much for inviting me. The committee is integrated by Mariella Dimiccoli from Universidad, Politècnica de Catalunya, and Dr. Daniel Michelsanti, is that right? From Aalborg University, and myself, Martín Rocamora, from Universidad, República, Uruguay. And so the schedule we have today, we are opening the session now, and so Venkatesh is gonna be presenting for about 45 to 60 minutes, and then we are gonna have a round of questions, okay, by the committee members, right? Anything else I should mention?
Presentation, you come to go to the first row.
Yeah, I don't know. I'm fine here, but we can sit there. Okay. So I think that's all. If Venkatesh is ready, the floor is yours, and thanks very much for presenting us your work.
Thank you.
Oh, we should do that.
Hello, everyone. Firstly, I would like to thank all of you for being present here. It really means a lot to me. Thank you so much for being here. Thanks to the committee members for accepting our invitation. Thanks to my PhD supervisor, Dr. Gloria, Haro. I am Venkatesh, a PhD candidate at Universitat Pompeu, Fabra. Today, I will be defending my PhD thesis titled Towards Audiovisual Deep Learning Methods for Singing Voice Separation and Lip Synchronization. Here's an outline of the presentation. I will start off with an introduction. Then I will move on to 3 specific research problems that we address in this work, namely audio-only music source separation, audiovisual singing voice separation, and then detecting lip synchronization. I will wrap up this presentation with conclusions. We address 2 main research problems in this work, that is music source separation and detecting lip synchronization. In music source separation, the goal is to isolate the constituent sound sources present in audio mixture. Let's listen to an example. This is the mixture. There's the drums, which has been isolated from it, bass, voice, and the rest. So as we heard in this example, each of these musical instruments have different sound characteristics. So because of this difference, it is possible to approach music source separation in music mixtures like this by using the audio-only modality. Among the different musical instruments present in music audios, we are particularly interested in the singing voice in this thesis. For instance, let us consider a mixture of voices. Let us listen to it to get an idea how it sounds. So here we are interested in isolating the individual voices present in this mixture. These are the different voices present in that mixture that we are interested in isolating. So here in the mixture of voices, unlike what we saw in the previous case, the voices have very similar sound characteristics, and it is difficult to isolate the voices in a mixture like this just by using the audio modality alone. So what do? We go audiovisual here. So the audiovisual modality provides rich information by the means of lip voice synchronization information and also the identity information of the singer, which is useful in singing voice separation. In this particular example, we see that all the 4 voices belong to the same singer, so the identity information is not so relevant in this particular example, but in other examples where there are different singers involved, identity information could also be useful in isolating voice of the singers. From this point, we move on to the lip sync detection. So here the objective is simple: to have a model that can tell if a given pair of lip motion and the voice audio are synchronized or not. Very simple, right? Such lip sync detector models have different applications. Among them, in this particular work, we are again interested in using it for audiovisual singing voice separation, which is the main theme of this thesis. Now we get into greater detail into each of the research problems that we address in this thesis. We start off with audio-only music source separation. The goal here is to isolate the sound sources present in the input music audio, but the focus here is to do it in a low cost and low resource setup, which is more suitable for academic groups, I imagine. So we start off with we use this data set called MuseDB to train this music source separation model, which comes with the ground truth sources along with the input mixture, the mixture music audios. So since the ground sources are present, it allows us to train the music source separation system in a supervised manner. Also, the ground truth sources are present in 2 different settings, that is 2 source setting and 4 source setting, which allow for 2 different types of evaluation that we will see later. The dataset also comes with a predefined split of train and test subsets. The music source separation systems can be categorized into 3 types. Type A is a system of single input, single output models where each model is dedicated to isolate a particular type of source. Type B system is a single input, single output model, but it has a source specific conditioning applied which dictates which kind of source has to be estimated. So, and then in type C system, we have a single input multi-output model. So here this model is capable of estimating multiple sound sources present in the input music audio simultaneously, which is very convenient. Now, as we move from type A to type C, we see a reduction in the amount of trainable network parameters. And the type C system has the least amount of trainable parameters. And this kind of system is suitable for our low cost, low resource objective. And in fact, one of the contributions of this work is our model, which belongs to type C system. And then we take candidate models from each of the other 2 types and compare how our models compare against the performance of the other 2 models from the other 2 types. For the type A candidate, we choose a dedicated unit system where each of the models is a unit. Here, the total number of trainable parameters of the system is equal to the number of units used in the system and times the number of trainable parameters in a single unit. Note that this system of units can be trained in parallel, but it adds to the memory cost. The unit accepts input mixture music audio spectrograms, magnitude spectrograms, and then it estimates a soft mask, and which on multiplication with the input magnitude mixture spectrogram gives the output magnitude spectrogram. This alone is not enough to get back the estimated audio of the source that we are trying to estimate, because the phase information is missing. A common trick that is used by the research community is to use the phase information from the mixture, and it works pretty much. And for this work, we choose the mixture spectrogram phase in combination with the output magnitude spectrogram. We do the inverse short time Fourier transform and get back the estimated audio waveform. For type B system, we take conditioned unit, which comprises of a unit and a control unit. Here, the number of training iterations increase because for every input music audio, we need to apply a source-specific conditioning. We need to loop over each of the conditioning specific to each of the sources. So the training iterations increase. Also, the inference time increases because of the same reason. And this control unit introduces additional trainable parameters that add to the training cost. What we propose is multi-channel unit, which is a type C system. So with the which is capable of estimating multiple sound sources present in the music audio simultaneously. With the multiple outputs arises the multitask loss function that we see here. And here, each of the loss terms is Li is defined as L1 loss on the magnitude spectrograms. And as I mentioned earlier, then the models estimate soft mask, which on multiplication with the mixture magnitude spectrogram give the estimated magnitude spectrogram for that particular source, which we use for computing the L1 loss with respect to the ground truth magnitude spectrogram. Right. Note that in this multi-channel unit, the computational cost is almost the same as that of a single input, single output unit, regardless of the total number of sources to be estimated. It's almost the same. So we get a lot of benefits by using an architecture of this type C type. Let us see how it fares in performance in comparison to the other two models soon. But before that, now that we have a multitask loss function that we saw earlier, we need to discuss how to determine these weights for each of the loss terms. A simple thing to do would be to have unit weights for each of the loss terms. What does it mean? It means that all loss terms are considered equally important. And we call it a naive unit weighting scheme. Then we have dynamic weighted average scheme, where the weights are dynamically determined such that a loss term that decreases faster is assigned a lower weight. Okay? Now let us look at the energy distribution across various sound sources present in the music audios from USDB18 dataset. In the two-source setting, we can see a clear difference in the energy distribution between vocals and the accompaniment. In the four-source setting as well, there is a difference in the energy distribution between vocals, drums, bass, and the rest, but it is more subtler. It is more prominent in two-source setting. And we observe that the models tend to learn better to isolate the sources which have higher energy values. So based on this energy distribution, we explore the energy-based weighting strategies to determine the weights in the multitask loss function. So here, the first one coming up is Ebw P1 weighting scheme. Let's understand what it is. So P1 is for power 1, okay? And here, the weight for ith source is determined as a ratio of a reference average energy and the average energy of the ith source. Ebw inst P1 is very similar to Ebw P1. There is just this inst term here. What does it mean? It stands for instantaneous. And as you can see, there is a t component. The weights vary with the time. So for every iteration, the weight is computed with respect to based on the ratio of the instantaneous reference energy value and that of the instant energy of the ith source. We have next Ebw P2, which is again very similar to Ebw P1. Here there is P2 for power 2. So as you can see, the energy terms here have been raised to power 2. So that's the only difference. And finally, we also compare another energy-based weighting strategy called, which was proposed by O et al., where there are two constraints. One constraint is that the weight times the energy, average energy for that particular loss term, for that particular source is constant across all the sources. And another constraint is that the sum of the weights is unity. Okay, so we compare all these the model's multi-channel unit trained with these different energy-based weighting schemes. Now, moving on to the results, we first discuss computational cost for various models considered in this work. So we can see that the YUM unit, that is multi-channel unit, is a better choice in terms of computational cost. It is very low computational cost in the sense that it is having lesser number of trainable parameters, and it takes lesser training iterations per epoch to train than compared to dedicated units and conditioned unit. And also it has faster processing rate at the inference. So this model, as I mentioned earlier, is suitable for our low cost, low resource setting. Okay. Now let's see how it fares against the dedicated units and conditioned unit. Here in this table, we report the results of music source separation in the two source setting. Okay, so the two sources are vocals and accompaniment here that we are trying to isolate from the input music mixture. Only the results that are statistically significant with respect to the dedicated units results are dashed. Okay. So one clear observation that we can make here is that the conditioned unit performs very poor in comparison to the dedicated units and the multi-channel unit in terms of SDR, which is a source to distortion ratio metric commonly used in music source separation to evaluate music source separation models. The YUM unit, all these are different variants of YUM unit, which we saw are trained using different energy-based weighting schemes. We see that these models perform very similarly to each other. But if you want to point out something, we can say that the naive unit weighting based model performs slightly poorly than others. But another interesting observation is that look at these two models like Ebw P1 and Ebw Inst P1, like they perform even better than the dedicated units. So if we were to recommend make a recommendation here, we would recommend to go for YUM unit trained with energy-based P1 strategy or Ebw Inst P1 strategy for the two source setting, which even outperform the dedicated unit system. Let's listen to a demo example before we move further in this direction. So here we get to listen the voice, ground truth voice, conditioned unit voice estimate, and Ebw P1 voice estimate. Okay, it's there. So, if we listen to these samples very closely, we will see certain artifacts and missing harmonics present in the conditioned unit estimate, which is not a problem in the Ebw P1 estimate. More examples are put up on the project page. Okay. So now we discuss the results from the 4 source setting. Here there are 4 sources: vocals, drums, bass, and rest. In the interest of space, because of space constraint, we put up only the SDR median values here. A detailed tabulation of results can be found on the project page. Again, we only show the results which are statistically significant with respect to the results of the dedicated unit system by dashing them. Okay. Again, first thing to notice here is that the conditioned unit performs poor also in the 4 source settings in comparison to the dedicated unit system and the unit variants. But here the dedicated unit system performs the best for vocals and bass, while some of the unit models perform the best for drums and the rest, and if we consider the overall metric. So it is difficult to pick one model from multi-channel unit and to say that this is the best in the 4 source setting. So yeah, since we picked Ebw P1 model in the 2 source setting, for consistency, we just choose that as the selected candidate in the 4 source setting as well. But notice that in the 4 source setting, the M unit doesn't perform as good as it was performing in the 2 source setting. And this we attribute to the energy distribution chart that we saw earlier. There we saw that the energy distribution between voice and accompaniment in 2 source setting is very different, but the differences are subtle in the 4 source setting. No? So the models are able to profit from this relative energy differences in the 2 source setting, and M unit performs better there. So this is an observation that we made. Now let's listen to a demo example from the 4 source setting. Here we listen to the ground truth base, condition unit base estimate, and Ebw P1 base estimate. Okay, it's the differences are more subtler, but if you listen with headphones, you will notice that there are certain interferences in the condition unit base estimate which are not there in the EM unit estimate. Also, there are certain artifacts that are shown in this spectrogram in the condition unit estimate. Again, more examples can be found on the project page. In conclusion, multi-channel unit is a cheaper alternative to condition unit and the dedicated unit system, which is one of the themes of this work: low cost, low resource setup, right? It is faster than unit at inference, conditioned unit at inference. And as I mentioned earlier, the energy based weighting scheme is effective when the sources to be isolated have significantly different energy values, right? The source code and the demos can be found on the project web page. Now, after looking at the what we can achieve in terms of music source separation by using the audio modality alone, as I mentioned earlier, when we move to combination of voices which are present in music audio, it's difficult to isolate the voices because the voices are having similar characteristics, right? So that is why we are exploring getting some help from the visual modality, right? Because when you look at someone singing, you can look at their lips moving. Also, you get some idea regarding the identity of the person, and you kind of have an idea how they might sound, right? So visual, that's why we explore the audiovisual singing voice separation topic. So again, the motivation here is when you have a multi-voice video, music video like this, given a target singer's face, we are interested in isolating that person's voice from the mixture. Note that the sequence of frames, the visual frames are more useful than the static ones, because the sequence, using the temporal sequence of these visual frames will give you the motion information, which is an important cue in isolating voices in multi-voice videos of this type. During the time of our work, we didn't have a data set to train such an audiovisual singing voice separation model. So we built our own data set called a cappella, which contains around 46 hours of a cappella solo singing videos taken from YouTube. The songs are set to 4 language categories: English, Spanish, Hindi, and others. The dataset also comes with the predefined splits for training, validation, and test. This dataset is suitable for training models for applications like audiovisual singing voice separation, audiovisual singing style transfer, and lip voice synchronization. And the model architecture that we propose is YNet here, which is basically a UNet conditioned by visual features at the bottleneck. The YNet accepts complex spectrogram as an input, and it outputs complex ratio masks. And in the previous work, we were outputting soft masks, which were only helpful in getting the magnitude spectrograms. But from this point, we found complex ratio masks, which also estimate the phase of the output audio. So some research works have shown that complex ratio masks have shown to work better in speech separation, because the phase is also estimated by the model, and in the speech works, they showed that if you use the mixture phase rather than estimating separately for the output, phase separately for the output, it gives rise to robotic effects. So with this complex ratio mask choice, we can do better. And for the audiovisual fusion block, we choose film layer, which does the linear combination of the audio features coming from here and the visual features coming from here. We explore 2 different variants of the YNet architecture. First one coming up is YNet M. The M stands for mouth. So basically the input here is a sequence of cropped mouth frames, RGB frames. And the visual encoder to process this RGB frame sequence is a reduced version of the mixed convolution 3D ResNet, which basically comprises of 2 3D blocks of convolutions and 2 2D convolution blocks. This kind of architecture is helpful in extracting the motion information, which is useful in isolating voices. Okay. The other option that we have is YNet G, another variant of YNet, which is the G is for the graph. Here the input is, the visual input is a sequence of phase landmarks, which are fed to this visual encoder, which is a spatiotemporal graph convolution network. Note that, again, in the enthusiasm of the low resource, low cost ideas that we had, this is a lightweight representation. There's the phase sequence of phase landmarks, a lightweight representation in comparison to the RGB frames, which are very heavy and it occupies a lot of space and memory. And yes, the visual encoder here is a lightweight model, which is reflected in its number of trainable parameters, right? And as opposed to this 3.1 million is not much, but it's still a lightweight model here, only 1.3 million parameters. So this goes in the theme of the low cost, low resource interest that we had. And to compare these models, we consider several baseline models, which are trained again on our a cappella dataset for fair comparison. We choose an audio only baseline, which is just a unit without any visual feature input. Then we also consider a Llcp model, which is which was a state-of-the-art audiovisual speech separation model at the time of this work. The key differences of Llcp model with respect to our model is in terms of the visual front-end representation. We use landmarks or RGB frames, but they use something called face embedding, which is extracted by a pre-trained recognition, face recognition model. And also the difference is with regard to how the audiovisual fusion is done. In their case, they just concatenate the audio and visual features along the temporal dimension. Also, they use a recurrent neural network module, BLSTM, which we don't use in our YNet. So these are some key differences. Now we get into how we train our models. We use a self-supervised training setup which falls in the mix and separate paradigm. There are two different types of mixtures, audio mixtures that we encounter. One is the one lead voice type, where voice sample from a cappella dataset is mixed with a sample accompaniment music sample from AudioSet or MuseDB to artificially create a mixture. And this accompaniment music belongs to the categories like background music, beatboxing, choir, lullaby, rapping, and so on. Note that the models YNet-M, YNet-G, Llcp, and UNet are trained on samples obtained using this setup. Then there is two lead voice setup. Here, there is an additional voice sample present which is taken from a cappella dataset. Sorry for the lag. So now the models YNet-MR and YNet-GR include mixtures of type two lead voices while they are trained. In fact, it's trained with 50% of samples coming from two lead voice type of mixtures and another 50% with one lead voice type of mixtures. And we may wonder why to have this kind of 50% mixture, different type of mixture. The motivation behind doing it is to have a single best model that works for one lead voice setup as well as two lead voice setup. The loss that we use here is mean squared error between the target and the estimated masks, complex ratio masks. Yeah. So now we discuss a bit about the evaluation setup. We consider three different test subsets: seen, heard, unseen, unheard, and multi-voice video. We also consider three different evaluation setups, where for the first one is one lead voice mixture, where the mixtures are only containing one lead voice, and then in the other two lead voice evaluation setup, there are only two lead voices always present in the mixture, and we also do an evaluation with variable volume levels of the target voice in the mixture. So we can imagine that in a group of people speaking together, someone who is speaking with feeble volume, feeble voice is more likely not to be heard. People don't understand what this person is saying, right? So that's why the real test of how the audiovisual models can really profit from the visual motion is can be really understood based on how they work when the volume level of the target voice is low. Here the visual, the lip motion becomes really crucial, motion information becomes really crucial. So that's why we also have this evaluation setup. And okay, just to wrap up this slide, the toughest setups here are, of course, the multi-voice video, where there are more than two singing voices present, overlapping singing voices present in the mixture audio. Of course, this combination is also particularly tricky. The combination of unseen, unheard test data with two lead voice mixtures and the low volume of target voice. So these are particularly challenging setups for evaluation. Now we dive into the results one by one. Okay, in the results we show the performance of these models on different test subsets that we saw earlier: seen, heard, unseen, unheard, and multi-voice. So what is this multi-voice? So this multi-voice video is something that we put together and published along with this work because we wanted access to the ground truth voices, the voice of each of these faces. And also, unlike the seen, heard, and unseen heard subsets, where the mixtures are produced artificially by randomly combining some accompaniment music with voice, here they have some musical relation. This is why we with this kind of video, real world multi-voice video, we can have, since the ground truth voices are available, we are able to evaluate them using this SDR metric, which otherwise would not have been possible because the videos in YouTube we don't get these individual voice audios, right? So one quick observation that we can make, among many other things, is that the performance in seen-heard subset is better than unseen-unheard. Yeah, of course, the singers that were encountered during training, the model is more comfortable in isolating their voice in the during the evaluation. Much more easier, so seen-heard is much more easier than unseen-unheard subset. And notice that there are some new languages in the unseen-unheard subset. What is it? So this is basically others category here, but these were the languages that were not even encountered during training, like totally new languages. So that is why we just make a distinction here. And the most important observation to be made here is that the Ynet GR performs the best in terms of SDR on overall. The Ynet M performs better than Ynet G, but the irony is that Ynet GR performs better than Ynet MR. So Ynet M and Ynet MR are the same models, but the R variant had this special training setup where 50% of the mixtures were taken from 2-lead voice setup. You're right, if you remember. So as I mentioned it earlier, likewise, Ynet G and Ynet GR are the same model, but they are trained in a different way. R is for remix, and it's like 50% of the time in the R variants during the training, they have 2-lead voice mixtures, and other 50% time they have 1-lead voice mixture. So what does this mean? This means that the Ynet G model is able to profit more from the visual modality when it has been trained with 2-lead voice mixtures. So now we show some results on the volume analysis. So here we list the different volume levels of the target voice that needs to be estimated. We report metrics based on SDR and SIR, which is like source to interference ratio, and greater the values of these two metrics, the better the source separation performance. First, we discuss the results of volume analysis in the 1-lead voice setup. So in the 1-lead voice setup, the Llcp model performs the best at volume levels. The Ynet G and Ynet GR models perform the second best. But the most important observation in this 1-lead voice results is that Ynet GR performs better than Ynet G when the target volume level is the lowest. So this blue color is lowest volume level. So, so this shows that motion information is important even if there is only one voice and to be isolated from the accompaniment, it is still useful. Moving on to the volume analysis results in this 2-lead voice setup, here we can say that Ynet GR models perform the best at all volume levels. And it is evident that motion information is important, particularly in 2-lead voice setup, because there is another overlapping voice that makes it challenging to isolate a particular target singing voice. Now let us listen to a demo example. And this is a real world mixture that we take from YouTube, and we are interested in isolating this target singer's voice. Okay, this singer was not encountered during training. He's a random, unknown, unseen, unheard singer. And basically, if you heard it closely, he was saying, you are leaving the crackle. We want to isolate that voice. And let's listen to the estimates of all these different models that we have. So, of course, none of the estimates are perfect, but if you want to pick, you can see that our Ynet M and Ynet GR models perform better than the other two baselines. Of course, more demos can be found on the project page. Okay, let's summarize what we have seen so far. We provide a new data set of a cappella solo singing voice performances as a part of this work, which to our knowledge is the first public audiovisual data set for singing voice separation. We also provide a new audiovisual singing voice separation model called ViNet. We show how the audiovisual methods improve upon the audio-only methods in challenging evaluation setups that we saw. And also, our method performs better than the baseline models in the two lead voice setup, which is the highlight of this work. So now we move on to the part where we discuss the work on our work on lip synchronization, which is the last part, research problem that we worked on. So what's the objective here? So we have a sequence of input sequence of video frames and the audio. The goal is to detect the lip synchronization in speech and singing voice videos. So we mentioned speech and singing voice. So let us first try to understand what is the difference between speech and singing voice. For this, I have put here example of speech and singing voice samples from male and female participants, which share the same lexical content, that is Edelweiss, Edelweiss. Let's listen to the female example.
Edelweiss, Edelweiss.
So there are certain wavy patterns that we can see here in the regions where the singer elongates or sustains the vowels. This, in fact, corresponds to a musical ornamentation element called vibrato. Such patterns and such ornamentations are typically found in singing voice and not in speech. And these sustained vowels are typical of singing voice. So these sustained phonemes make it difficult to detect if a lip motion and singing voice are synchronized or not. It's easier to detect lip voice synchronization in speech where these ornamentations are not there, and it is difficult to detect the lip synchronization in singing voice. Okay. Now we speak a bit about the architecture of the model that we propose. We call it vocalist, though only part of it is vocalist, but yeah, let's get to it. It comprises of audio encoder, visual encoder, and audiovisual synchronization block called vocalist. The audio encoder is a stack of 2D convolution blocks with residual skip connections. The visual encoder is a stack of 3D convolution blocks here because we need to process the motion information. So it's 3D convolution, stack of 3D convolution layers with residual skip connections again. And for this audiovisual synchronization module, we have vocalist, which is based out of which is comprised of cross-modal transformers. It comprises of mainly 3 cross-modal transformer encoder units. The A2V unit takes in audio features as the query. The key and value comes from visual features. The V2A unit takes in visual features as the query and the audio features as the key and value. The hybrid fusion blocks takes in the output of A2V block as query. The key and value are sourced from the output of V2A block. So now we move on to the training setup used for training this model. We again use a self-supervised training approach where the model is trained for audiovisual correspondence. So what is it? So basically, if for the positive examples, which is in sync audiovisual pair of input, and negative example, which is out of sync audiovisual pair of input, the model should maximize the audiovisual correspondence score for positive examples and minimize this correspondence score for negative examples. We use a binary cross entropy loss function to train this model. Both the positive and negative examples are sampled equally from during the training, right? So now moving on to the experimentation section. So we conduct experiments in 3 major parts. First part here is lip synchronization in speech. And as we said earlier, we also study lip synchronization in singing voice, which is harder than speech due to sustained phonemes or vowels. And then again, as I mentioned in the introduction, the theme of this work is audiovisual singing voice separation. So all this, in the end, all this lip synchronization work, we dedicate it to the singing voice separation application. So with regard to lip sync in speech, we use the LRS2 dataset. The evaluation protocol here is that the synchronization in voice video is considered to be correctly identified by the model if the detected offset is between -1 and +1 visual frame. So what is this detected offset? This detected offset is nothing but the relative displacement between, in terms of visual frames, between the audio sequence and the visual sequence that gives the highest audiovisual correspondence score. Now, with regard to the lip sync in singing voice, we use a cappella dataset. And in the evaluation protocol, again, we use a very similar protocol as we used in the lip sync in the speech version. But here, the model is said to have correctly identified the synchronization if the detected offset is between -5 and +5 visual frames. So why this difference? Earlier we saw -1 and +1, here -5 and +5. Why? This is because the evaluation criterion is relaxed in case of singing voice than compared to speech, because as we discussed earlier, detecting lip synchronization in singing voice is more difficult, and even a state-of-the-art model, state-of-the-art work also uses the same evaluation protocol for singing voice. So it makes sense. And this is also based on what humans observe. Like if you give voice audio and singing face visual, if the difference is within ±5 frames, humans cannot really distinguish if there is a problem of lip voice synchronization and singing voice, right? So, but in speech, you can easily find out because speech is a different kind of voice. So this is reflected in the evaluation criterion as well. So again, finally, the main theme of this work, singing voice separation, for that we used a cappella dataset, and we discuss it later. First, we discuss the results of lip synchronization in speech. This is our model right here, and it performs the best in terms of accuracy of lip synchronization, detecting lip synchronization in LRS2 dataset. It outperforms all the baselines listed here, but it comes at a price. We have the highest number of trainable parameters, but it works better than the rest. So all the listed model here are trained on 5-frame context, that is 0.2 seconds, which is very small temporal context, but that is used typically for training the lip voice synchronization models. But then the question arises, how do we train it, how do we evaluate it on larger window context like 7, 9? If we train it on 5-frame context, how the evaluation is done on larger context? So let me give one example because it's easier conveyed through an example. Suppose we have a 7-frame long input sequence. We consider the 5-frame snippets within this 7-frame sequence, and we compute the audiovisual correspondence scores at different offset for each of these snippets. And then finally, we average the audiovisual correspondence scores across the 5-frame snippets. And then what we have? We detect the detected offset corresponds to the index with the maximum averaged audiovisual correspondence score. That's quite a mouthful, but yeah, this is how this process can be extrapolated for the larger window context of evaluation. Now we discuss a bit the results of lip sync in singing voice. First thing to notice here, the performance drops. Look at these values, like 50s, 60s, and 85 is the max. And here we saw like 90s, like, you know, like this is, this could be because we have two possible explanations for this. One is clearly that lip sync detection in singing voice is harder than in speech. Despite the relaxed evaluation criterion, it doesn't perform as great as lip sync detection in speech. But another potential reason for this could be that a cappella dataset is a small dataset. Like it is 46 hours long and LRS2 is like 226 something hours. So our a cappella singing voice dataset is like 5 times smaller than a speech dataset. So probably we didn't have enough singing voice samples to train this lip synchronization model. Could be another explanation, but yeah, this needs to be verified in future work, but yeah, this is what we have for now. And one of the baselines that we use here is SyncNet star, which is an improved variant of SyncNet. And we have this var column, which indicates if the model was trained on variable length input. For example, this vocalist model here was trained with variable length input. So what does it mean? It means that to evaluate on a 10 frame context, we use the model which was trained on 10 frame context. So for 10 frame evaluation, we use 10 frame input. For 25 frame evaluation, we use model trained on 25 frame, right? So that is what we mean by this var if it is trained with variable length input, as opposed to not training it that way, which is what when we don't train it with variable length input, we use the averaging mechanism that I illustrated in an example of 7 frame, right? So, and it is clear that the models which are trained with the variable length input perform better than those which are not. Another observation here is that the gains in the improvement here, passing from 5 frame to 10 frame, 10 frame to 25 frame, is much larger in singing voice than what we saw in the speech. In the speech, like we were starting with 92, 93, and it grows very slowly, and it reaches up to 99. But here it jumps from 58 to like 85. So the gains are large. So potentially with a larger data set, we could get better performance from these models. But anyways, here the best score of 85.2% we get with the vocalist model trained on 25 frame context, that is 1 second length audio, trained with variable length input. That is, it was trained with the 25 frame context of audio and visual information. Yeah, and now let us listen to this application of audiovisual singing voice separation. So here we are interested in isolating this target singer's voice. We choose the following audiovisual singing voice separation baselines. Ynet MR that we already saw. I won't revisit this again because in the interest of time. As we discussed earlier, the visual encoder in Ynet MR is a reduced version of mixed convolution 3D ResNet. Now, the idea in this work is to replace this visual encoder from Ynet MR and plug in the visual encoder of the lip sync model. And how do we do it? We use the pre-trained visual encoder which was trained from the lip sync model, which was trained for the lip sync task. And then we freeze its weights and we refer to it as Ynet MR V. There is a V thing, no? Yeah. So here are the results of audiovisual singing voice separation. Here we highlight, we show the dotted results only where the results are not significantly different from the Ynet GR. So we speak a bit on this later. Note that Ynet MRV with the pre-trained weights of the visual encoder from the vocalist model performs the best among these models, which are basically the models that operate on RGB frames. Ynet GR operates on sequence of landmarks, but among the models that operate on RGB frames, our model performs the best. An interesting observation here is that the same model, if you don't use the pre-trained weights and freeze it from the vocalist model, and if it is trained end-to-end, it performs poorly. This is an indicative of overfitting. This could be probably because, as I mentioned earlier, a cappella is a very small data set, and this is like 80 million parameter plus model. Like it can be very too big a model to train on such a small data set, so it tends to overfit, of course. But what this shows is, if we use the pre-trained features model from the lip sync visual encoder, we perform much better. This shows that the visual features that was learned by the lip sync model was very useful, even if it is on a very small data set like a cappella, right? And last remark here is that these results are not statistically significantly different, so we can say that this model performs comparably with YNET-GR, which is a model operating on sequence of phased landmarks. So let's listen to demo example with YNET-GR, YNET-MR, and YNET-MRV estimates. The thing to focus here is this region, where the singing voice is silent, and none of the other models estimate the silence better than our, in fact all are ours only, but in this work the highlight is this model. So none of the models get the silence as good as the YNET-MRV model. So in summary, we have a new audiovisual transformer-based lip voice synchronization model, which we call Vocalist, which gives state-of-the-art results in both speech and singing voice for lip sync detection task. Lip sync detection in singing voice is much harder than in speech because of the sustained phonemes in singing voice. Our model learns powerful visual features through the lip sync detection task, which we use it for singing voice separation. Okay, so coming to the last part of this presentation, conclusions, let's go through an overall summary of what happened, what we saw. So we started off with audio-only source separation, where the main contribution is a low-cost model for simultaneously estimating multiple sound sources present in input music mixture audio, and also we propose a novel energy-based weighting scheme for training the multitask model in audio modality alone. So, and then we saw why audio-only approaches might not get us far when it comes to these kind of voice mixtures. So we explored the audiovisual singing voice separation task, and we noticed how visual modality can help in isolating voices, overlapping voices in such scenarios. We also saw a new state-of-the-art audiovisual model, YNET. We also published a new data set to promote research in this direction, which is called a cappella, which is publicly available. And finally, we saw lip sync detection. So here we proposed a new state-of-the-art lip sync detector model, which works on both speech and singing voice contexts. And we also show that, okay, this lip sync model is not learning something useless. It is the features that it learns through the visual modality is useful in guiding singing voice separation. Okay, so coming back to our low cost, low resource theme, so we identified the following solutions throughout this work. As we saw earlier, multi-channel unit performs comparably to that of dedicated unit system and conditioned unit at a much lower training cost. And in this part, the second part, we saw phased landmarks from a cheaper alternative to RGB video frame sequence. Besides, it also allows for better generalization and are less prone to overfitting. Finally, from the lip sync module, we saw that knowledge sharing between models trained for different tasks can be beneficial. Even if the data set is very small, we saw how they shared their knowledge, learned from different tasks, but still it helped in singing voice separation. So, of course, our work has a lot of limitations, and the main ones we list here in the interest of time. That is, we need human evaluation to support our results, because the metrics are not enough. The source separation results in particular, they need to be evaluated by humans, and such an evaluation is very expensive, so we couldn't fit it within the PhD timeline, but this is important as well. There are several failure cases for our singing voice separation model, So as you can already guess, and some of you might already have thought, so let's listen to this. So here the problem is that all the lips sing in a synchronized manner. The lexical content is same, they are just harmonically different from each other, but it's difficult to isolate voices in these kind of mixtures where the identity of the person is also the same and the lip motion is also the same. So there is not much to profit from the visual modality in these cases, but there could be potentially audio-based methods which study the musical relation between the different voices, like tenor, soprano, alto, so which is elaborated in music theory. So maybe such methods could be better than audiovisual methods, but yeah, we didn't focus on these kind of samples. Here are some pointers for future work. We could train with mixtures obtained by adding a voice with a time-delayed version. So this is a much harder example because you take a voice and add with its time-delayed version, so the singer identity is same. It's just that the model should be really paying attention to the synchronization when you train it with mixtures of this type. Also, another thing to do would be to train models by checking for consistencies in the estimated sound characteristic. For example, suddenly in the sound estimate for the first 2 seconds, my voice is isolated. In the next for the next 3 seconds, someone else's voice is coming. Okay, then the model can be trained to see, okay, look, this is a different person's voice, so do something else. So this information can be used potentially to improve the work of singing voice separation. Also, from the lip motion, we can deduce silence. So none of these models are perfectly silent when the lips are silent. So what we could do is we could train a model just for the silence detection and then just set the volume level of the estimated voice to be 0 and get an instant boost for all the existing models by just deducing silence from lip motion, right? So we can also use information from multiple singing phases simultaneously. Okay, with regard to future work in lip synchronization, we could do evaluations on smaller variants of vocalist, which is like a huge model, and we might not need that, but we couldn't do it because of time. We could explore lightweight architectures operating on phased landmarks. And also we could try training with contrastive losses like info-NC loss, where multiple negative examples are used along with a single positive example, and some works use this, and we could also explore it in future. Okay, so with this, we are at the end of the presentation. Here is a brief summary of contributions. Note that the source code and demos are made available for each of these works. And here are some workshop contributions. I would like to thank you for your attention and for coming here today and being a part of this event of my life. Thank you.
Thank you very much, Venkatesh. Mariella, please, you start.
First of all, thank you very much for your presentation. It's been very clear, and you had time to go into details for many issues. And also to say that it was very pleasant and engaging to read your manuscript. And in general, I appreciated very much the global coherence of your work because you could make connection between the different contributions. And in particular, for instance, when for the lip synchronization, you could find application again to the singing voice separation. And for each, also find that you did a considerable lot of experiment for each proposed model, and this is very useful to understand the limitation and the potential of the model. What really allow us to learn a lesson and advance the state of the art. And I appreciate also the critical analysis that you made in the conclusive chapter of your thesis, and also you outline a lot of potential future line of research, and also the systematic effort that you did to make the code and the data publicly available, because which is really valuable to have this already done at the end of the PhD. And so altogether, I think that you leave it to the community as a very valuable piece of work that will contribute to advance the state of the art in sync weight separation, lip synchronization. And now I have some questions for each chapter. And so, for instance, in chapter 3, you proposed a method for using sound separation for audio only. And then you proposed a weighting strategy that allowed to take into account the energy of the signal to avoid bias, no? But here it seems that when the number of sound sources increases, then this doesn't work very well. And I would like to know if you consider to automatically learn this weight, for instance, by using a kind of different mechanism, no? Because there you just propose some heuristic.
Yeah, it's true that when the number of sources increases, it becomes more challenging to isolate any particular source. And yeah, so there could be definitely better ways to figure out the weights of the loss terms. And basic idea remains the same still, though, that there are competing loss terms which, like, I will reduce first, you know, and then we need to know that, okay, the network always has this tendency to cheat in the sense that it will try to reduce the loss term, which is like very simple to reduce, the tasks which are easier to learn. So for that, yeah, so there have been some new weighting schemes for training multitask loss functions that we would love to try. But the one that we tried was dynamic weighted average, which was dynamically changing weights based on you know, like how the loss terms are being reduced. So we did do some analysis in that direction, but in the end we saw that that's dynamic weighted average result that we saw, and it doesn't outperform the dedicated system, and probably it could be the limitation that maybe it's not possible to get better than dedicated system. So dedicated system of models, this is a multitask model, right? So yeah, maybe it might not be possible to do better than the dedicated system of dedicated models. So of course we need to do more experiments in this direction.
Yeah, so you think that the fact that you are using a multitask approach is a limitation for this?
Yeah.
Yeah. Because there also the thing is that you are trying to reduce the cost, the computational cost.
Yeah, yeah. That's the main highlight. So, yeah.
Okay. And so regarding the data set you introduced in chapter 4, so you said that one limitation is that it is small size, relatively small size, and if you had the opportunity to do a version 2 of this dataset, what feature you will add?
The thing is, this was a lot of manual work in the sense that me and my collaborators, we started searching on YouTube, and you know, like, it was a lot of manual work to put together these videos. But from latest computer vision literature, we find that people put together like Llcp and huge data sets together by using a YouTube crawler, like a script to crawl through the videos and automatically to have automated pipelines that kind of understand what's the audiovisual content in the videos, and you know, like, so definitely I would love to use that kind of approach, automated approach, to browse through the videos automatically and to have a computer vision based pipeline which filters videos based on what we need. So and that way it will do much better than manual browsing of videos, because YouTube is huge, and you know, using this kind of pipeline will enable to have much larger data set and also more variety.
More variability.
Variability as well, yeah.
And do you think that it will be too much costly to add ground truth for human evaluation?
Yeah, the thing is, humans can also be biased, and the problem is, sorry, with regard to the audiovisual work or in general?
Yes, because you also constated that limitation of your work. You don't have the perceptual evaluation.
Yes.
And this is something that is missed in the data set, and
Right.
it's a feature that could be added and will add a lot of value to it. So you think that this will be very costly or could be done for?
Yeah, the thing is, human evaluation is very expensive because it's already difficult to have few people to sign up for it, and if you have lesser number of people, there is a risk of bias and is not enough. So there are methods set up by the music source suppression community, like they recommend things like Mushra, which is a particular kind of test which also dictates how, in which condition you have to do the test. There shouldn't be disturbance, and also at different volume levels and things like that. So these things are very elaborate, and to be honest, like most of the works that are published in this community these days, they do not include human-based evaluation. And that the irony is that these metrics themselves are not reliable, because I saw one example where the metrics of the SDR are same. The music source suppression evaluation metric SDR is same for two estimates, but one of them is much better than the other. Humans perceive it better. So there are always problems like this, and yeah, it's true that human evaluation is not done as a part of this work, but we will need human evaluation to strengthen and to strengthen our claims, and also to make our results more reliable.
And so when regarding the design of the cross-modal transformer, you said in your manuscript that it's inspired to a recent work, but it's not very clear the difference, because you didn't go into this. If you could explain this point.
Which one?
The cross-modal transformer. So you said in the manuscript that it's inspired to a recent work. So, but it's not clear what are exactly the differences.
Yeah. So in the manuscript, thanks for the interesting observation. I couldn't cover it in the slides, but yeah. So the idea of cross-modality that inspired me was from this emotion recognition work from, I don't remember the reference exactly, but in this work, they use cross-modal transformers in the sense that there is key, query, and value, right? So they use 3 such transformers, and they also use audio, visual, and text modality. So there is for each transformer, they use combination of 2 modalities, and then finally they combine all these pairs of 2 modalities into something very hybrid, hybrid information from all these 3 modalities. And so the key observation here was that they were able to do emotion classification, which is a classification task, which is what I am also doing in a different way. We are interested in classification, and we are interested in cross-modal fusion. So these are the 2 inspirations that I took from their model architecture.
Okay, thank you. And so you said that one of the tasks that could be enabled by your a cappella dataset is also style transfer.
Yeah.
Yeah, and do you think that, for instance, because then you demonstrate also that sharing information between tasks is beneficial? So do you think that, for instance, solving the task of style transfer could lead to improvement for other tasks, for singing voice separation and synchronization?
Yeah, of course, because in the end, what we want is we want models which are careful observers. Like we want them to observe the content, to make connections between what they see, like to make relation between the voice and the face, also sometimes also the lip motion. So I think in general, all these possibilities are possible where we train a model for a particular task, which then learns all these connections between voice and this correspondence between audiovisual modalities, and then of course we could definitely have more chances that what it learned is useful for some other audiovisual computer vision task.
Okay. And so just an observation, because I have seen that as a visual information, you said just the movement of the lip or the facial landmarks, But do you think that could be useful to use more contextual information, for instance, and visual terms, I mean? Because, for instance, when a person is singing, you can see really a lot the movement of the neck, around the neck, but I think there is nothing about this. Do you think that could be useful to have more contextual information, the shoulder, the neck, and...
Theoretically, I imagine that, yeah, it should, any kind of information that is there, like eyebrows, lifting, throat, all this potentially could be useful. But the problem is that what we noticed was that when we also had a model trained with full face rather than just cropped frames, and it had very high tendency of overfitting. So we need to figure out how to change the model architectures that we have in order to come out of this overfitting. Just because there are more visual features, it was overfitting and it was not giving good performance in the evaluation sets. So we didn't go in the direction of exploring full face based works.
Okay. And okay, and so you proposed several future line of research. Which one do you think is more promising? So if you had time to do another paper, for instance, what you would work on?
It's difficult to answer because everything is equally tempting, and because I see, the thing is, we just started this, this was the last work of my PhD, and I see promising directions in all of them, because I found inspiration for each of these listed future directions from existing works which were not really related for singing voice separation. So to pick one in particular depends. For example, if I want to do something else and just put some experiment to train that, I would choose something like use a different loss function. There's like just a minor change and it will train, then I don't need to think about it. But if I really want to think about this, I would consider reducing the lip sync model size, because it's 80 million parameters, and I'm kind of having thoughts that is just exaggerated. We don't need such big models. And the thing is, by the end of my PhD, I had access to a workstation with a powerful GPU. So I was like, okay, now I can also do royal stuff and I can increase the size of the models. So I just did it for that reason. But I think I will spend some time to make lightweight version of the lip sync model that we have, which operates on face landmarks, and rather than the RGB frames, and see if it can still give better performance.
Okay, I like your answer because actually, as you yourself said, the number of parameters of the last model came as a surprise, because with all the low-cost consideration before, then it was a bit a surprise. So it would be nice to conclude by having this low-cost model for the lip synchronization also.
Just to add what you said, yeah, there is also a low-cost component in this last work, because the low cost is with regard to the data set. So data set is very small, so it's like doesn't take much space. So the yeah, I agree that cost-wise our model is not very good, but in terms of data set, we showed what can be achieved with a small data set, which is a low-cost memory setup, right? So yeah, just to complete.
And finally, I want just to ask you what do you consider yourself is the bigger contribution of your thesis?
That's to be honest, like as a PhD student, I started getting more into the field over the final year. So I started with the audio-only music source separation, and then I think the audiovisual works is more something that I really I'm happy with. The way it's there were no applications before that were, I mean, in the sense that it was not very common to see applications of singing voice separation and these things, and it really excited me to work in this field. So I would say that I'm more interested and happy about the audiovisual singing voice separation work. But again, I don't see the lip sync work as a different thing. It is a part of the main problem is that. So.
Okay, thank you very much.
Thank you. Okay, so it's your turn, Daniel.
So thank you for the presentation. It was nice, clear, and the thesis was very good reading. Yeah, I wrote a report as well, so if you want it, I can give it to you later. I don't know if you have access to this, but yeah. I have some questions. I don't know if it's possible to see the
Sure.
thesis. Yeah, so it's
The
way
thesis.
easier. Otherwise, we can just do.
My laptop got stolen, so I don't have
Yeah,
access
yeah.
to that. Okay.
It's fine. Well, yeah. I will just then
But
try
I
to
can.
say what. No. It's just fine.
Okay.
It's fine. So in the introduction, you mentioned that speech and singing voice are quite different from each other, right? So you develop some models that can work with both, right? More or less, at least some models that you show can work with both. What are the features of your model that make it good to work with both? Because if I just look at your models, right? Or also at any other models that the community propose. If I just change the data set, right? So I train on speech, then that model would be good for speech. If I train it on singing voice, that model would be good for singing voice. So what do you think that your model is good for both? Or, I mean, what are the features that make it good for both?
Yeah, first of all, such a comparison is difficult because, as I said, LRS2 is a 5 times larger data set than a cappella, so we cannot really compare this. But what can be compared is a model that is trained on LRS2, but then applied on a cappella, and we publish in the results that we publish. There is this part, for example, the row 3, if you notice in the screen. So this model was trained on LRS2, and it still worked, it's in fact worked better than the model trained on a cappella, which is the next row, with the non-variable length input. So you see, like, when the data set is big, it provides a lot of help in this kind of task. And we didn't take any special consideration for singing voice than speech, except for the evaluation criterion, which was relaxed for singing voice because it's much harder, and pre-existing work in the literature does that. But as I said, it works for singing voice as well as speech. What I mean with it works is that it works this way, like it gives very poor performance. But the thing is, no existing work before compared the performance of speech sync models on the singing voice. So that way we just say that, okay, we are the first ones to our knowledge to try this, and we report what we got. So, but it doesn't mean that ours is the best. Maybe ours is the best because we are the first to do it, but we do not really take special considerations for the singing voice evaluation. But that is something that we would have loved to do if we had a bigger data set. We couldn't expect much from a small data set like a cappella.
Yeah, so now we are in this slide, so I can ask also a specific question about here, right? Don't you think, you compare this one with also the speech performance, right? And with speech, you saw that it was around 92%, right?
Yeah, for the 5 frame, yes.
Yeah, so don't you think that the problem is, the issue that you experience here is inherited in the problem itself, meaning that speech has a very high variability, right? So when you evaluate, for example, using the 0.2 second, then you can capture the variability of speech. Yeah. But in voice, in a singing voice, you have this sustained vowels, for example, right?
Yeah.
Then you cannot, there is no way that you can capture in 0.2 seconds.
Yeah,
so do you expect that even training with different model or whatever, you would rise that 50% to 90, or is just maybe a problem an issue of the problem itself?
The problem in singing voice is that in fact, using uniform length context might not be the most desirable option. We must be interested in places where the lips are changing. For example, if we are doing ah, and if you cut the in between where I'm doing ah is not so useful part, but when I start the transition is a very useful part. So what would be interesting to do in future would be to identify the places where these changes are happening, rather than choosing a bigger window just like that.
Mm-hmm. Yeah, yes, I agree. So I have some, I just find in the thesis because, yes, so basically you mentioned some kind of masks and loss function in your thesis. Now, yeah, you do it in the background, but also, yeah, you mentioned also before in the presentation. And at a certain point, I noticed that you switch from an L1 loss to an L2 loss. What's the reason for that, and why L2 works better? I mean, why did you decide afterwards to use L2?
That was just because, in fact, there were works, I think one of your own work, which analyzed these different loss functions. Besides that, we saw that the existing works in speech separation, which is the main inspiration for the work that followed this audio-only music source separation, started using this L2 loss. So we just didn't really get into the ablation on the kind of loss to choose, and we just followed what was the norm being used in the audiovisual speech separation community.
Yeah. Yeah, so about landmarks and complexity in a way. I would like to that you comment on this, because you said that using landmark, your model is computationally less complex in a way.
Yeah.
But don't you think that you are just moving the complexity? Because you need to get the landmarks from something, right? So, and I guess that what you do is you use some network to detect the phase, to track it, to extract the landmarks. So you're actually hiding the complexity here. You're just showing landmarks, but you need to get landmarks somewhere, right?
Yeah, this is exactly what we were asked by one of the reviewers, and it's a very interesting question. The thing is, when we say this crop mount frames, or if we use the visuals, inherently we use a landmark detection, because we need to register the faces, because we need to align them. And though the RGB frames in fact hides in itself the landmark detection. So the problem is the other way around, not the landmarks itself the problem. The problem is using the frames requires the extraction of landmarks before you really align the face, you know. So that way sequence of landmarks is always computationally cheaper.
Yeah. And yeah, so in yeah, I think you have some tables with some results where just pick one table. Yeah, maybe not this one, but well, in some tables also in the thesis you report some statistical significant results.
Yeah.
What kind of test do you perform to get?
I use the Z test, which takes an assumption that the distribution is normal, but yeah.
Yeah. And then just one last question. You mentioned before about the main contribution of your thesis, but what do you think would have like the most impact in 5-10 years time?
In fact, the lip voice synchronization, I'm already getting interest by different companies who are like they don't care about the cost, but just because it does better, they are really, because now we are getting into an era of talking face avatars, and you know, so where the heart of these models is to have a very good lip sync model, and whichever is the best state of the art, everyone is interested. Of course, it comes at a big cost. So I think this is at the moment very hot in the market. I hope it answers the question.
Okay. Yes. Thanks.
So that's my turn. First of all, I'd like to summarize some of addition of your work, which I found really interesting. I'm gonna repeat some of the comments of my colleagues here. But it was really a pleasure to read your thesis. I used to work myself, not my students, myself, in the problem of singing voice separations long time ago. So it's nice to get into the problem again, and I really appreciated the challenges you were faced to, because in the past I wouldn't dare to try to separate singing audio in this kind of scenario in which you have several singing voices. And I think that some of the points you have in your thesis perfectly motivate the idea of using the audiovisual clues, and I found this really interesting. I think that the thesis has a real deep understanding of the techniques that are used, in particular those related to, well, the audiovisual representations, the data you use, all the things related to the machine learning techniques that are applied, and congratulations for that. Another thing that I really liked is that despite the fact that you consider different, let's say, different tasks, different problems, as the other members of the committee mentioned, and even yourself, the thesis is really coherent, and it's very nice, those last results you have, in which the lip synchronization task is actually useful for guiding the singing voice separation. So I think in general terms that you have a really solid, nice piece of research work. So congratulations for that. And I also have some questions and some, if I'm asked to criticize the work, I have perhaps two main concerns that maybe you probably agree, because you mentioned some of that in your presentation too. The first one is related to not having perceptual evaluations of the methods you propose. I'm completely aware this is a lot of work, but let me say, like, just as an advice, I myself in the past, I was very reluctant to do subjective tests, because of course this is a lot of work, but over the years I somehow tried with other colleagues, and I would say that it's not of course it's a pain, but it's not so hard, and it really adds a lot to the scientific quality of your work. You already say that you are aware that those objective measures are not so useful in different cases, and so having perceptual evaluations open up also the opportunity to criticize or to go deeply into the discussion of the results you get. So I think it's something that should be taken into account. And my other, let's say my other, by the way, these two concerns that I'm raising here should not be regarded as a detriment of the quality of the work, but maybe as I was saying, as some suggestions for improving the work. And so my second concern has to do with the evaluation of the methods, the singing voice separation in the audiovisual singing voice separation with artificial mixtures. So I'd like to ask you if you could be explicit about the limitations of that, and what sense you think they are artificial, and that in what sense that could be, let's say, beneficial to to the evaluation to consider a more real scenario.
Yeah, so we had to stick to this mix and separate paradigm, which artificially mixes voice with accompaniment. So the point here is, yeah, it's not the real world mixture, but that's the only option that we had to train our models, because we didn't have access to data sets like which contain multi-voice mixtures with individual voices. But that said, looking at what the lip sync model does, and also some works related to audiovisual correspondence in the past, what they do is they mix the audio with its own time delayed version. So what happens is the network, if you want to isolate one of these things, the network really has to look at the audiovisual correspondence to isolate a particular voice. So in this sense, it is advantageous to have the artificial mixtures, but to prove this point, I will need to evaluate on many such multi-voice videos. Our models, our existing models which are trained with artificial mixtures, need to be evaluated on many such real-world multi-voice video mixtures, which we try to do in the demos, but still it needs human evaluation because we don't have access to the ground truth sources. So I still think that since there is not just the audio modality here, there's also visual modality which tries to track the mapping between lip voice synchronization. It can be useful to have artificial mixtures, but the real test would be to say something concretely, would be to see how they perform in the real world mixture.
Yeah, thank you. I agree with that. I mean, of course, there's some evidence that doing this artificial mixers is useful for training. It's like a data augmentation approach. But my point was that, of course, you are aware that you don't have the harmonic coherence and the, let's say, the temporal, the rhythmic coherence that you would expect in real-life music. And I guess, unless this should be tested or proved, I guess those cases could be more challenging, the case that you may have overlapping partials, overlapping harmonics, overlapping events in time. So I think that a real mixture is the real way of evaluating that.
That's true, yeah.
But I understand the challenges of that, of course. And well, related to this, I should say also that one of the contributions of your work that's really valuable is in data sets. And perhaps that one of the things that would be useful in the near future, and maybe then by other researchers. And you stress the fact that, to the best of your knowledge, there's no public available data set of this kind. Of course, it's really rare to have video and also audio and separated audios, separated meaning singing voice and accompaniment. But I found a paper that is from the transactions of ISMIR, the journal, from researchers from the University of Rochester, that was published roughly, or without the roughly, exactly at the same time that your paper on the British Vision workshop was published. So it's perfectly understandable that both groups were not aware of the work by the others because they were working at the same time, exactly at the same time. But of course, well, I was curious about if you were aware of that work, and well, and if you are aware of that work, I'd like to some comments on maybe two aspects. One of them is the methods, which I compared to yours and have my let's say my opinion on that, and also to the data set, because I think it's some of the data set that that they have. Some of them is quite similar to a cappella, but some other data, they did recordings with people singing and video and audio recordings. So please.
Yeah, we were aware of this work not at the beginning of the research, but
sure,
at the time of publishing, because to say something strong as to our knowledge, we are the first is a big deal. And so what happened was this, we know this group from Rochester, and I think it's a paper with the first author, Bochen Lee, I think. So
Bochen Lee. Exactly.
So we were following their website for dataset. They said that they released this. I think it's called UR-Sing dataset.
Yes, UR-Sing.
Yeah. So until some months back, the download option was not there, and it was not publicly available in that sense.
Oh, you mean they had the paper available, but not the data set?
So it was not public. So in that sense, we are the first. But yeah, I could have. I think I mentioned it in the manuscript that it's included in the manuscript. I mentioned that this Bochen Lee group also had a similar data set, but it was.
I didn't find it. You might check it then.
Okay.
Okay, and do you have an idea of the
differences? Yes.
Differences of the methods and also the data?
One particular difference, I think they recorded something in their own studio setup. Ours was more like in the wild, what we find in the wild. That's one difference. And another difference is that in the evaluation, we focus more on the volume-based analysis, which they don't do, which is which is very important, because when there are multiple speakers and someone is speaking feeble with low volume, we are interested in isolating them. And this is a real litmus test, I would say, to see if the model is really paying attention to the lip motion and audiovisual cross-modal features, because that way it will have to take the supervision from the visual modality and then try to estimate that voice. So that particular thing I remember was not there in their work, but besides that, I don't remember much.
Yeah, so may I help with that? So they have this also this kind of approach of searching YouTube videos, and this is exactly the same as you did, and they also did random mixtures. But they use the random mixtures only for training, not for. They use them mostly for training, and they use in some specific experiments. They only use the UR-Sing dataset, the one which has the separated voices for evaluation. They have 65 pieces and 22 singers, and it's also small.
Yeah, it's much smaller.
Okay, that's an important point. I mean, it's only 4 hours, so you may not train a system with that. But
evaluation,
as we were discussing earlier, it would be nice to use it for evaluation.
Right. But it was not available at this time of work.
I see. Yeah. That's important to know. Great. Perfect. And and regarding the methods, do you remember any differences or similarities?
I don't know if they also trained with this 50% of where mixtures where 2 lead voices are present, and 50%, because we wanted to have one single model that performs in both single voice isolation as like one lead voice separation and in 2 lead voice. Our objective was that, and our vision at that point was to increase the number of voices, and it was something that should work that we should be able to extrapolate to multiple voices. So based on my reading at that point, I couldn't find this kind of vision there to have this kind of intention while designing the training setup where you have 50%.
Yeah, I agree. I also think so. Okay, and regarding the video front end, they don't use they use the frames cropped around the mouth, and they don't use your graph neural network for processing face landmarks, which is also an important difference, I guess.
Right.
Okay. Cool. So what time is it? I have a couple of. I have several questions and some suggestions, but let me just select some of them. Yeah, remember we talked about perception. I would just suggest that it would be nice to consider in the weighting of chapter 3, in the weighting of the losses, you consider only, let's say, the energy and the dynamics, but this energy is actually distributed differently in the spectrum for the different instruments, and this is somehow related to timbre, and it could be beneficial I guess, but
in fact, we used it. That was the first work. In the second, the audiovisual singing voice separation. In the loss term, we used something called gradient penalty in the loss term, which penalizes again based on the energy distribution in the spectrogram. It penalizes more the loss terms where the differences are more in the high energy regions differences. Okay. So yeah, there was something like that we considered, but not in the weighting scheme, but in the audiovisual singing voice separation.
Okay, so I missed that.
Yeah.
Right.
Sorry, couldn't cover it in this.
Right. Yeah, I was thinking of something like learning, as she said, learning the weights, and those weights could be learned according to the energy distribution across frequency, which is something that is somehow quite frequent in the audio processing field. Okay, I have already praised the challenging tasks that you consider, and I may comment on the most challenging ones, which are several voices at the same time, singing voices at the same time, maybe even of the same person. So this is really challenging, right? So you mentioned at the end of your presentation that perhaps audiovisual is not enough in those cases. So what kind of other information in the context of music do you think it could be useful, or I mean, I'm not saying that you have a data set and that it would be practical, but just thinking of it. Yeah.
There are some interesting works already in the audio only method. When you say audio visual is not enough, maybe we don't need audio visual. Audio alone is enough in this aspect. In one possibility that I think of right now. For example, this group at Music Technology Group, they published work, this data set of soprano, alto, tenor, bass, choir, which has a lot of, and they also published works for audio only based separation, source separation in these kind of choirs. So it's possible to use such data sets and train using audio modality alone. But another interesting work that I found recently was with the score. Generally, there is in the score it's notated the harmonic, the different voices, and then this could also become another cue to isolate voice of particular type.
Okay, I agree. That's the two things I was thinking of. So that's great. Okay, so I have other questions that are really low level. I think we may discuss them in person if you want. Let me ask one of them.
Sure.
Just one of them. In the synchronization stuff at the end, you use the model, the visual model, which crops the mouth.
Yeah.
And you say that, but the model that actually performs best is the one which is based on the landmarks.
Yeah.
No, meaning in
the previous, yes, right.
Okay, let me frame it better.
No, I understand.
Okay, in the last part, when you consider again the singing voice separation, guided by the features you learn from lip synchronization. Is it
Yeah,
that
yeah, got
clear?
it.
Okay, so the question is, wouldn't it be possible to somehow combine those things in the sense that you may use the landmarks for lip synchronization, and also then the landmarks, the system that does singing voice separation in that context would be using the landmarks. I mean the features learned, but not from the images, but from the landmarks. Would it be possible? I am missing something there. What was the motivation for starting with other? I guess the video encoder, but what was really the motivation of that?
I think the question has many parts, but the most critical that I find here is that why did I not train the lip sync detector with landmarks as input? So in fact, I did try that, and it's very tricky to use the existing spatiotemporal graph convolution network module, and I tried to use the landmarks to train something similar, a similar kind of visual encoder, but it was not working for some reason. And the thing is, I still need to study more about the graph neural networks. It was just this STGCN was just out of the box implementation which was available. So it's to analyze these kind of aspects that you pointed out, it needs more in-depth knowledge about how these architectures can be improved for a different task. So when I tried lip sync detector with the graph landmark based front end, it didn't work for the architecture that I used. But of course, it doesn't mean that it doesn't work with the it cannot work with landmarks. I will have to spend more time in studying what kind of architecture could be used. That is why I put it in the future directions, which that is this network alone is like 40 million parameters, this visual encoder that we see. The one that we have in the graph neural network is not more than 10 million parameters. Even the light one that we saw here was like 1.3 million parameters. So I think we will have to study how to have increase this 1.5 million parameter graph neural network to 40 million, but by making sure that this big model actually does what we want and not does overfitting and yeah. So for that, it needs a different kind of thought process, I guess.
I understand. Thank you. Okay, I think we finished. Do you have anything else to add? No. Is it time to invite the audience? Yes. So I should invite the audience. Any member? Yeah. Yes. Yeah. Anyone? Sorry. Thank you. Anyone with a PhD in the audience that wants to ask a question or not? Not? Okay. Thank you. So I kindly invite you to leave the room in order to deliberate. Thank you. Okay, so the committee has been deliberating. I'm not going to repeat all the praises that we had before about the thesis. In general, we think that it was a really good piece of research. The thesis has substantial contributions in many aspects related to very relevant problems and addressing really challenging scenarios, and has several contributions related to the state-of-the-art methods that were proposed, and also the creation and the public release of new datasets that for sure they're going to be useful for other researchers to come. And so the presentation was really, really good. We were very satisfied with the interaction, the questions we did, and the answers you have. And I think that's it. So we come up with a grade of excellent, and we have proposed to vote for the cum laude. That's going to be known, I think, in some days.
Okay.
That's it. So congratulations. It was really a pleasure to read your work and to be aware of your work, and to be here in person for doing this, for attending this presentation.
Thank you, everyone.
Thank you.